Roughly one-third of the food produced in the world for human consumption every year, approximately 1.3 billion tons, gets lost or wasted. While food waste has considerable economic costs, it is also one of the largest segments of municipal solid waste, resulting in significant global environmental consequences. A 2013 study by the Food and Agricultural Organization of the United Nations entitled Food Wastage Footprint: Impacts on Natural Resources found that each year, food that is produced but not eaten uses the same volume of water equivalent to the annual flow of Russia's Volga River. The study further found that food waste is responsible for adding 3.3 billion tons of greenhouse gases to the planet's atmosphere annually. Solutions for the reduction of food waste are complicated. There have been suggestions for less production. However, there are ethical concerns that there are already 795 million people who are undernourished worldwide. Further, by 2050, it is estimated that the world's population will reach 9.1 billion, and in order to feed this larger population, food production must increase by more than 70%. Nearly all of the predicted population growth will occur in developing nations, where there are already concerns about inadequate food consumption and high levels of undernourishment. There are government and corporate initiatives to regulate food waste, such as the US EPA Food Recovery Challenge, the EU Waste Framework Directive, and the public Flemish waste management company's food waste management hierarchy. However, no real impact has been made in the reduction of food waste thus far. In addition, not all food waste is equal in its environmental impact. Two studies in Sweden in 2015 and 2017 examined the environmental impact of the waste of various types of foods. It was determined that bread waste had the largest contribution in total mass, resulting in the greatest ozone depletion, freshwater ecotoxicity, and resource depletion. More than 95% of the bread that is wasted ends up in landfill sites, where it is converted into methane by anaerobic digestion. The effect of bread waste is significant, as methane has a much greater global warming potential than carbon dioxide over time. As such, the bread waste stream was found to have the greatest potential for reducing greenhouse gas emissions as compared to all other food categories. As it is difficult to determine consumer demand, bread and bakery production continues to have significant waste. In seeking to reuse bread and bakery waste, some waste can be repurposed into products such as breadcrumbs, or as a replacement of some flour and sourdough, or as an animal feed. While the reuse priority is given to people in need, due to microbial spoilage, reuse or repurposing of bread and bakery waste may be risky to consumer health. These concerns have led to the examination of repurposing bread waste for a purpose beyond consumption or landfill material. Bread waste, with its high concentration of nutrients, has been examined as a commercially viable organic substrate for dark fermentative hydrogen and ethanol production. In addition, bread waste has also been studied as a monomer of bioplastics and as a substrate for the biological treatment of wastewater. Currently, bioethanol is the most widely generated biofuel. Bioethanol is produced most commonly from corn in the United States, wheat in Europe, and sugarcane in Brazil. As these crops are regularly consumed, there are concerns that the consequence for their use in biofuel production results in increased food prices and creates additional food scarcity for developing nations. One solution has been to use agricultural or forestry residue as a possible substrate for bioethanol production. Yet the conversion of these residues results in processing difficulties, and the ethanol yield from them is much lower in comparison to starchy or sugar crops. Several studies have examined the fermentation of waste bread as a substrate for ethanol fermentation, finding that waste bread was the best choice for high-efficiency industrial ethanol production without increasing food prices. To produce bioethanol from waste bread, the starch, lipids, and proteins must be converted to monomers. Converting these macromolecules into glucose, fatty acids, and amino acids requires enzymatic hydrolysis, which increases the cost of production. So several studies have sought to determine the most effective conversion process with the highest ethanol yields. Some initial studies demonstrated the possibility of this process using flatbread, wheat flour, and wheat rye bread. While bread production and storage could significantly change its raw ingredients and reduce the suitability of bread as a fermentation feed, all were successful raw materials for ethanol production by fermentation. Further, increased efficiency was obtained with the use of supportive enzyme preparations. More recent studies have examined the optimum conditions for bioethanol production using sliced white bread waste obtained from an on-site refractory at the University of Manchester, United Kingdom. Using a novel process developed at that university, based on the production of hydraulic enzymes from a small portion of waste bread via solid-state fermentation, a nutrient-rich hydrolysate could be used to create bioethanol through subsequent fermentation. One study used a multi-enzyme solution rich in glucoamylase and protease developed from waste bread pieces using the fungus Aspergillus awamori. Optimum conditions for fungal growth and enzyme production were determined. The heterotrophic fungi were used as they are good at breaking down complex macromolecules such as proteins and lipids. A second study by the same university expanded on this research by examining whether coupling solid-state fermentation with the availability of an ideal substrate such as waste bread could provide simultaneous glucoamylase and protease production, thus resulting in significant bioprocess enhancements. In addition to bioethanol production from waste bread, biohydrogen production has also been studied. Conventional hydrogen production technologies demand high energy inputs. However, biological hydrogen production is relatively efficient with relatively low energy demands. Dark hydrogen fermentation produces hydrogen by breaking down organic compounds. Yet due to the cost and low hydrogen yield, this process was not considered viable for industrial application. Recent studies in 2016 and 2017 have begun examining the efficiency and effectiveness of using waste bread as a feedstock in dark fermentative biohydrogen production. These studies have included data on the economic viability of this process. Most recently, a study reported in the January 2017 Journal of Cleaner Production has further built upon the prior research on dark fermentative biohydrogen production. The study suggests that simultaneous dark fermentative hydrogen and ethanol production from waste bread is possible. This study focused on continuous hydrogen and ethanol production in a mixed pack tank reactor using waste bread as a substrate. This study demonstrated a potential bioprocess for hydrogen and ethanol production from waste bread that is both economic and efficient. The estimated world annual production of bread waste of 10 million tons per year could provide substrate in an efficient manner as compared to current raw materials. A bioprocess for simultaneous hydrogen and ethanol production from waste bread has the potential to decrease economic and environmental costs. In addition to the use of waste bread for the production of biofuels, studies have also examined the production of succinic acid from waste bread. Succinic acid is a necessary component for many chemical substances, including those used in bioplastics. Seeking to move away from the current succinic acid production using petrochemicals, a fermentative succinic acid production using waste bread as a feedstock has been studied. The study compared succinic acid production from other materials including wheat, corn cob, potatoes, and orange peels. The findings in this study demonstrate that the succinic acid yield per total sugar in fermentation using bread hydrolysate is higher as compared with traditional chemical production. An additional study has since been done examining the economic viability of a succinic acid production plant using bread waste. Bread waste has also been examined in the biological treatment of wastewater. The biological treatment of wastewater uses microorganisms that require a feedstock in order to be effective. An examination of using waste bread and skim milk for this nutrition has been studied. While skim milk alone can be used as a source of nutrients, it is an expensive system. It was found that bread waste in a composition of skim milk could be recycled as a source of nutrients in the biological treatment of wastewater in a cost-effective manner. With a growing population and food waste a continuing economic and environmental concern, the repurposing of waste is required. Bread waste, as the largest mass of food waste, can be repurposed to produce biofuels and succinic acid for bioplastics. Further, bread waste can be used to feed the microorganisms treating wastewater. The repurposing of bread waste, due to its fermentative properties, serves the dual purposes of reducing environmentally harmful landfill waste while also creating more environmentally friendly products. There is a cost and learning curve to implementing such new technology, yet the environmental outcome of failing to repurpose waste is a guaranteed continued degradation of land, air, and water. Thus, it seems clear that all waste, including bread waste, should be examined to determine how it can be viably repurposed.